questions. Really should have put that on there. Do you want the answer done?
Yes.
Yes, yes, yes.
All right, we continue with our second talk. Gleb Pogudin from Algebra State.
Okay, first of all, I want to thank the organizers for this nice event, and I'm glad to give talk here. So I'm going to speak about some differential analysis of the well-known fact from commutative algebra and algebraic geometry. So you can think about the just simple algebraic normalization in two ways: geometric and algebraic. Algebraic, it means that in any functional algebra, okay, here dividers. You can find algebraically independent elements such that A is integral over the algebra, which is generated by them. From the geometric point of view, it means that you can just, if you have an irreducible algebraic variety, you can map it surjectively onto find the space with find filters. So far, it seems that there is no appropriate notion of what is integral in the differential case. So maybe, moreover, there should be several different integral things in differential case, like several dimensions, as David Marker said. So what I'm going to generalize is a bit weaker version, when you, from the geometric point of view, you just want the map to be surjective. You don't want fibers to be defined. And speaking algebraically, you just want to have a listing property for prime ideals. So for every prime ideal in this algebra of polynomials, you want to find line over prime ideal. Just commutative algebras call this line over property, actually. And what I'm going to do, what I do, it's differential case. Actually, everything is turned out to be really the same if you have a differential algebraic variety of some dimension. We can map it surjectively on affine d space over K, and actually this map is defined over Q. And again, from the algebraic side, you can find a subalgebra which is isomorphic to the algebra of differential polynomials, such that your algebra is algebraic, differential algebraic over it, so they have equal differential percentage degree. And you have again a listing property for prime ideals. For every prime ideal in this polynomial algebra, you can find the prime differential ideal, which is line over it. Again, nothing really surprising, but how can it prove that? Actually, there are two standard ways to prove algebraic normalization lemma. I say that they are different. Actually, they're not so different. Both of them do some generic substitutions. The difference is what language do you use and what kind of substitutions do you perform. There is some algebraic approach that you add some high degrees of other variables to some variables, and that's how you get the integrality. Other approach is geometric. I've written down here. It actually constitutes of several steps which are in some kind of loop. You start with a affine variety and you want to decrease the dimension. You pass to its projective closure. You find the point outside the projective closure or at the infinity and project. It will be variety in a affine space of lower dimension, and since you project projective variety, you will get closed image. The point is that in differential case, there are two big problems with this approach. first big problem is that when you take practicalization of affine differential variety, it can contain the whole infinity. Moreover, it's almost always contain a whole infinity, so you can't fix that point for projection. The second problem is that in differential case, projective varieties are not longer complete. Okay, you know there's a big problem with complete differential differential varieties. There are not so much of them. So we follow the first one, and it's interesting to see. Okay, why this does work, but it doesn't. I have no any conceptual reasoning about this. I just a fact. Okay, maybe I will say something else about the proof after all. But now what I want to say is how the final map looks like. Actually, it can be thought as a composition of two maps. First, one map. Okay, you have X here. It's a very simple pattern. First, one map is an automorphism. Which is pretty nonlinear. And then you just project on the first big coordinates. So this part is quite tricky. It's not very simple. Automorphism is constructed some others, but general picture is like this. And what can we say in terms of differential equations? In terms of differential equations, we can actually say the following thing: that this means what is an automorphism? It's just a change of variables in differential equation. So you have some system of differential equations. Okay, you know that it defines some radical differential ideal of some percentage degree, and then you can perform such change of variables that this projection will be surjective. That means that if you pick random elements of the differential closed field here, you can extend this tuple to be a solution. That's what does result mean from some differential equation side. It's quite good, but not at all, because when you say to somebody who is interested in differential equations, hey guy, you will have a solution in differential closed field, he will not be very happy, because he has no idea what does it look like, this your differential closed field. So I want to obtain an analog of what I have said before with power series. In order to accomplish that, I want to say a few words of what does geometry over power series looks like. And I will tell some facts about that. They are not just my achievement, it's some well-known facts, but I don't know the place they're all collected, so it's like folklore. Everybody knows, but I don't know where it is. Okay, so let us restrict ourselves to algebras over complex numbers. Everything will work over other constant field, even over other differential fields, but there are some changes in the definitions. So, for simplicity, we deal with power series over complex numbers. And what do we have? We have such a homomorphism. It's not differential homomorphism, just evaluating at point 0. And this means that if you have a point over C of t, so if you have a point so you have a differential homomorphism from the coordinate ring of your variety to this differential algebra, you can easily obtain its differential point. You can obtain just ordinary algebraic point over C. you just compose this differential homomorphism with the evaluation 0. And interestingly, this implication can be turned upside down. If you have a homomorphism to complex numbers, you can construct a homomorphism, differential homomorphism to power series. You just use Taylor series formula. And it can be verified that this is a differential algebra homomorphism. So we have two implications. And that's why solutions in power series are interesting not only for differential equation people, but they are interesting for algebras because they mean just points over C, algebraic points over C. And this points over C of T or over C, they share some properties of points over differentially closed field. Actually, there is a kind of differential Nullstellensatz for these points. So, differential Nullstellensatz says that if you have some consistent system of differential equations, it has a solution in differentially closed field. Equivalently, if you have some finitely generated differential algebra, you have some homomorphism to differentially closed field. That's what happens with power series. Actually, for every differentially finitely generated C algebra, there is a homomorphism to complex numbers. It's important that algebra is differential because, okay, differentially finitely generated algebra is actually, in general, not finitely generated as an algebra, and it need not to have such homomorphism. But in differential case, it happens. So every non-empty over differential closure, every variety which is non-empty over differential closure is non-empty over power series. So it's quite reasonable to speak about this geometry. And again, this geometry also has normalization. Okay, the geometric statement is pretty the same, just I replaced my big K with power series. That's what's happening. In algebraic language, it just means that you have line over property for prime ideals which are not differential. So you can leave any prime ideal, no matter what kind of ideal do you have. Okay, so we have so far. We have two Noether normalization lemmas. And it is quite reasonable to want to compare them. I'm sorry?
So I'm just trying to think through the things that you've said. It smells very close to the statement that any radical differential ideal is going to have a differential 0 in this power series ring, but that can't possibly be true. The power series ring is not differentially closed. What am I missing?
Yes, because these ideals should be defined over C.
Got it, thank you. So over constants.
Okay, over constants, yes, yes.
Okay, got it, thank you.
So I start with some differential, defined over C. Yes, that's the difference. In general, if you have some equations over power series, they may not have solution power series. You know, it's quite easy to construct. Okay, so what I did, I wanted to compare. So I have another lemma over decay. I have a lemma over power series. In order to have some correct comparison, let us assume that this decay is a differential closure of power series, So if we have variety defined over C, and both lemmas give us some homomorphism which is defined over C, or over Q actually, and it can be surjective in this sense or in this sense. And what's the connection? One connection is quite well known. It says that there is such implication. So if you have a homomorphism of differential rings, if it is surjective on algebraic spectra, it will be surjective on differential spectra. This is stated explicitly in paper of Dimitrushyn. He did much more about the connection between differential spectra and algebraic spectra, but this is the part. Okay, this can be easily shown. And the inverse implication doesn't hold. And that's just an example. Let's look at this differential polynomial. It defines some variety in A2, and let us project it on x coordinate. No matter what x will you substitute here, it will be always non-constant differential polynomial. Because if x is not 0, this is not 0. If x is 0, this is not 0. But you can substitute such power series that it won't be solvable in power series. You just substitute minus t sub x, and you arrive to an equation like y dot t equals 1 is not solvable in power series. Okay, the reason is that you can define an algebraic homomorphism which vanishes simultaneously on both coefficients. Because from algebraic point, x and x prime are not related. So these points in power series, they don't know much about our differential structure, and that's the problem. So that's why the second lemma is really stronger than the first. And actually, it's quite annoying for me because I have two variants. First variant, I can prove this lemma and then deduce this, but it seems not the natural for people to live over differential closed field. And I also like differential closed field, and my dream is to prove something about differential closed field and then say, and some machinery allows me to deduce results over power series. But okay, there is no immediate machinery there. There might be some assumptions on the homomorphism which help me to write this backward implication, but I don't know. Again, finally, we have that another term, thus we can just make another corollary for differential equations. Here it is. That actually everything is the same, but we have some algebraic differential equations over C, and you can make some change of variables defined over Q, that after you substitute arbitrary power series on first D places, the system will remain solvable. That's okay. I'm not sure if differential equation people will be happy with that. I will test it in 2 weeks. I will give this talk in some differential equation center. But it looks much better from that testing point. Okay, I think I have plenty of time so far.
Nice question.
Yes.
So you have constant coefficients, but can't you do some new? Can't you introduce some new variables to cover the cases of non-constant coefficients?
Okay. If you start with that's a bit problem, because if you start with this equation, you can do any change of variables, it will not help. But if you have some power series coefficients, you say that are new variables, and you put some equations which define them, it seems that you can find some okay, I will show it on this example. In this example, you can substitute this single equation with a system, which tells that this is equal 1 and x is something like. And then I can apply lemma, obtain some change of coordinates. But in that case, I will have not t afterwards. Maybe I will have some t minus 1, for example.
That's okay.
And it's okay. So in the case when you do such streak, lemma will also shift the origin in order to make the equation solvable.
Who cares?
It's great, but okay. I thought about that for a while, but it's okay. This trick works if you have some polynomial coefficients. If you have an arbitrary power series, you should somehow relate them with each other also.
But you know, polynomial is complicated enough.
Okay. So yes, you're right. Okay, if we have polynomial coefficients, we have something like this, but we will also shift the origin, and the corollary will remain true. Okay. Just I have enough time to say a couple of words about the proof. I don't want to go into details because okay, if you start, you can't finish the details. So I'll just want to highlight some relations. The thing is that my substitutions, my automorphisms are non-linear, and that seems quite interesting connection because there is also a primitive element theorem for differential fields, which there is a problem if you have, okay, let's speak about C, if you have differential field extension, so F is differential field, and it's to the centimeter degree over C is finite. Okay, it's finitely generated. Then again, if you have constant coefficients, you in general cannot do what people usually do in algebraic independent theorem. You cannot do linear things. There is no linear combination, and you want to seek for some unknown polynomial in differential case. And this is exactly the same. So this proofs, just this proof and that proof, they rely on the same trick how to look for polynomials, how to look for unknown polynomial in some differential variable. Maybe I'll just try how I do it. I'm afraid that without context it might be not very clear, but okay, we'll test it. A couple of minutes for that. Assume that you want to, you have some differential field, and you have an element A. And you say that, okay, I want to have some generic polynomial depending on A. Let's call it ambiguous. Since I live in some differential field or ring, I need also to have its derivations. Of course, I can say that, okay, let us call it its derivation, for example, lambda 1. And okay, it is, in my mind, it is polynomial of A, and this is some polynomial of A and A prime. It's linear in A prime, of course, but then I differentiate more. And the problem with this approach is that, okay, number of variables is growing, and my differential algebra do not know that I keep in mind that this is polynomial of A. And that's the problem, and actually it can be overcame by the trick, and then you introduce again some new algebraically independent variables, and you say that you will differentiate them like chain rule does. So you will say that is a quantity. When you define the derivation like this, you will, first of all, you'll have that this is polynomial, this is the derivation of b of a, and this is again a polynomial of a, just of a, not anything else. And you will say to your differential structure explicitly, look, it's polynomial of a. And that's some core trick of the proof. Of course, there are some bunch of other details, but this is something which distinguishes differential life from algebraic life. In algebraic life, you don't need such polynomial, generic polynomials. In differential life, you need, and okay, of course, I also wonder if there is some conceptual explanation behind that. I can use this trick, but I can explain it in full details. That's all that I wanted to tell. Thank you.
Yeah. So it's about the sort of the map of differential varieties corresponding to the analog of Noether normalization that you constructed at the very beginning of the topic. So you had a dimension D differential variety, and then you mapped it surjectively to affine D space. Okay. So do you know any other properties about the map? Like, are there circumstances in which you can say that the map is open?
That's a big problem, because actually during constructing my map, I sometimes throw away some closed things.
Right. Okay.
And when I throw something away, I can no longer look after it. So maybe you can carefully analyze that things that I throw away, I don't throw too much. I'm quite an economic person. But okay, for something, and if you want some properties like this, okay, you can have them, I think, on some open subset. Because I throw away some closed subset. But not in the whole space.
I have another question then. So if you start with a special case, like if you assume, so we're working inside of some differential polynomial ring, but suppose for a moment that that our differential algebraic variety of dimension D that we started with was just given by polynomial equations, and it was an algebraic variety. But we're still looking at it as the differential idea.
Okay.
So in that case, could you prove that the map of differential varieties, could you prove that that map is open?
Okay, my map, my construction violates that starting condition. So it explicitly makes, at some step I make one variable to have higher order than all others in order to do some further manipulations. So if you want to, I think there could be some especially good theorem for that case, but I didn't thought about it.
Because probably like if you just as long as you throw away some points at the beginning, like you say, your map probably is open away from those points or something, and then but maybe those points that you have to throw away sort of only wouldn't affect the underlying algebraic variety points or something like that. Is that what you mean?
Oh yeah, I think this case should be analyzed somehow separately, because maybe for it, I don't know, but maybe if you do some just algebraic normalization for it, maybe can work.
Oh, definitely. I mean, like if you do resolution of singularities or something, and then start with an atoll map.
Just the usual algebraic non-normalization.
I don't.
It should be checked, or maybe it
But I
should
mean,
be some.
look, if you just starting with the fact that you have this surjective map with finite fibers to AD, then when you take the prolongations, that can get ruined because you have to start with an atoll map for the prolongations to be nice.
Yes, yes.
So and
She's right,
to
but-
get a map locally like that,
Okay,
you have
okay.
to have non-singular.
My map violates this initial condition, so it should analyze it if you want something better. Again, from the point of people for the differential equations, it's meaningless to start with algebraic variety. That's what it might be.
I mean, instead of formal power series, I guess you could also consider rather like Laurent series or algebraic closure.
Okay, for Laurent series, you do not have that connection between points in Laurent series and algebraic points. So, okay, from when you just think about different rings where you can solve equations for you, okay, power series, Laurent series, and state series are merely equal options. But when you think about some algebra, power series became really distinguished because they correspond to algebraic spectrum. And that's the special thing about that. So of course, I think they don't know how to relate power series to algebraic spectrum.
Just pure.
So it can do some variation and okay, just go up and so there could be some theory, but it should work again. That's less algebraic.
Can you, I mean, this is maybe related to what we were talking about before, but naively you might think if you start with the differential variety, then you can look at its prolongations and apply algebraic normalization to them. You might hope that they fit together, or so somehow this fails.
Okay, when you say when you do some normalization for prolongation, you will again will have some substitution, and it may happen then for say x prime and x2 prime, you will pick some substitutions, and algebraic number lemma doesn't care if they are compatible in differential sense. So it's you should usually take care of that, and it's not trivial.
Any other questions? Okay.
So as before, we have